right, we will get started, and we shall have a recap of what we have been talking about so far. We have so far talking about how we are using satellites to collect data, electromagnetic energy from the Earth's surface, and know that one of the main sources of electromagnetic energy is the sun. We know that the sun emits electromagnetic energy and yesterday we were essentially looking at energy interactions in the atmosphere, and we saw that as far as the energy interactions in the atmosphere, so that we had transmittance through, we saw that there was absorption that takes place in the atmosphere, and we saw some of the gases that are responsible for absorption, and then we saw that there was scattering, and under scattering we looked at Rayleigh scattering, we looked at Mie scattering, and we looked at non-selective. Let me just make it a bit clearer. Hopefully this makes it a bit clearer. So this is what we chatted about yesterday, energy interactions in the atmosphere. So this is what we talked about yesterday, energy interactions in the atmosphere, and so that is what is happening in the atmosphere. So we have our sun here, and we are saying that so when radiation is sent from the atmosphere, from the sun, some of it will be absorbed, some of it will be scattered, and the rest of it will be transmitted, and it will eventually reach the Earth's surface. So today we want to look at energy interactions on the Earth. So let me just add another page. When radiation eventually strikes the Earth's surface, we have a couple of interactions that occur. So in our energy, we have which is incident. So when the energy is incident on the Earth's surface, we have three things that occur, and they are all under the principle of, and so we're saying energy is neither destroyed or created. So when the energy is incident on the Earth's surface of the for our incident energy, and sunshine comes on the Earth's surface, some of it is absorbed, some of it is transmitted, some of it is, and so there are numerous examples which you should also by now be conversant with. Examples of absorbed energy. Energy is absorbed for chlorophyll. In fact, used by chlorophyll for food for plants or vegetative surfaces. When you are sunbathing outside, that is an example of absorption. When you put your clothes out to dry, the clothes absorb energy and eventually your clothes dry. So all those are illustrations, and you can look into literature for various other examples of absorption. Transmittance, the best example I can give is, the best example of transmittance is like when you look into a water body, or you look into a swimming pool and you can see up to the bottom. Your ability to see that is because light has been transmitted into that water body. Reflected energy, I'm sure you know this from your physics, and when you see a blue surface, it's because all other energy has been absorbed, but it's only the blue light which is reflected. So the way we say is that with our energy, incident energy is equal to some of that energy is. Could we please mute? Energy transmitted, some of the energy is reflected. One of the things that we need to appreciate is that relationship dependent, or we say their wavelength. So for example, when you see a green shack, it's because all the rest of the radiation has been it means that all the rest of the radiation has been absorbed, and it's only the red. If you remember our what did we call it? Our electromagnetic spectrum. It's only energy in the red part of the spectrum that is reflected. So that's what we mean by wavelength dependent. So what we are saying is that these interactions that occur depend also on the wavelength. So absorption occurs at certain wavelengths. Transmittance also occurs at certain wavelengths. Reflection also occurs at other wavelengths. Of all of these parameters, the parameter that we would want to evaluate for the moment is this one. This is the one we're interested, because when you look at our remote sensing process, incident radiation comes to the Earth's surface. Some of it will be transmitted, some of it will be absorbed, and the rest of it will be reflected, which is what the satellite looks at. So we can establish a relationship between the reflected radiation and the incident radiation, and we can have a ratio between reflected radiation and incident radiation, and this relationship is called, as you can see, it is a ratio, and all surfaces have a unique reflectance depending on wavelength. So for example, let us look at the relationship between wavelength and let's look at the relationship between wavelength and so we have blue, green, red, and infrared, infrared. We can even have our microwave. Let's look at our reflectance. Because it is a ratio, you'll appreciate that reflected energy can never be more than incident energy. Is that okay? Do we believe that? Because
yes, we do.
Yeah, because whenever we have incident radiation on the Earth's surface, some will be transmitted, some will be absorbed, the rest of it will be reflected. So this reflected energy will never be the same as this. So this ratio can only be, the highest it can have is 1. Do you see that? So we can have values from 0 to 1. Though some people express it as a percentage, but we have from 0 to 100%. And so when you look at blue, green, red, near infrared, thermal infrared, remember this is the visible portion. That means we can only see within this range. We cannot see in the near infrared, we cannot see thermal infrared, we cannot see in the micro, we cannot see in the micro, we cannot see there. So our eyes stop here. So let's pick an example of vegetation. What is the predominant color of vegetation?
Green.
Okay, so it means that if you reflectance of vegetation in blue is quite low, in green it is high, and then in red it is low. Not so. The low blue, the low green, red would be for the few cases where we have red flowers or some, but vegetation is predominantly green. Now remember, this is what our eyes can see. Now if we could see in the near infrared, we would find that vegetation has a very high reflector. So if we made a plot, it would be something like that. And we say that this is a spectral vegetation. Maybe we should add healthy vegetation. So a characteristic feature of vegetation is that we have high reflectance in the green, but we have a much higher reflectance in the near infrared. So if you could see in the near infrared, the eyes could see near infrared, you would actually see. So if we could actually see in the near infrared, you would see that vegetation is very bright, but we cannot do that. So how do we know this? We can measure the spectra of different surfaces using what we call a spectrometer. So how does the spectrometer work? It measures, you take a measurement to sun, and then you measure, look at a given surface, and then it will give you reflectance, and it will give you the reflectance for wavelength from maybe 350. The one we have in the department stops at around 800 nanometers. If you'd like to see how it works, you let me know. We make an appointment. For the person who demonstrates it is only here during the day. So, but of course, for the more fancy one, we can see the spectra from 50 nanometers all the way to 1,000 nanometers. So it goes all the way probably into microwaves to show how the spectra goes. So for vegetative surfaces, this is what we call it's characteristic of vegetation, because we have high reflectance in the green and very high in the near infrared. It will vary. That's how it will be. Now, different even within different vegetative surfaces, you will get the same, but maybe slightly different. And again, I'm talking of healthy vegetation. If you look at probably a dry leaf, it will be something like that, because there's no chlorophyll, there's no whatever, so it will be different. So as we mentioned here, every surface has a unique reflectance, has a unique reflectance vis-a-vis wavelength. And so we say that every surface has a unique, so you can get the signatures for any surface. You can get a signature for vegetation, you can get a signature for leaves, you can get a signature for grass, you can get a signature for anything whatsoever. And so that is essentially what we use. That is essentially what we need to appreciate about the energy interactions on the Earth's surface. The fact that different surfaces have different reflectances, and actually what we're trying to do in remote sensing, especially when it comes to mapping. Now, in the remote sensing, we're interested in mapping and what we refer to as bio-optical modeling. In mapping, we want to identify, distinguish different bio-optical modeling. We want to relate value by your parameter. So when it comes to mapping, we essentially want to be able to distinguish one surface from the other. And how is that possible? And how is that possible? We take advantage of the fact that different surfaces have different reflectances. So I have let's say water, I have soil. If I am operating in the near infrared region, you'll see that you are looking at the near infrared. Vegetation has a higher reflectance compared to soil, which has, and then water has nothing, the near infrared. So by looking at the near infrared image, the brightest images will be vegetation, the less bright ones will be soil, and the black one will be so when it comes to a satellite image, when it comes to a satellite image, your brightest pixels will be vegetation. I'm just giving a hypothetical value. Say we're using an 8-bit sensor. This one 5. Hopefully clearer. Yeah, we looked at radiometric. Just a minute. Sorry, I had to sort out something here. So your values, which would be 0, would represent water, and then your middle areas, your areas which have an. Remember, this would refer to data collected in the infrared region. So we are able to distinguish the water areas, from, so this is your water area, this is your vegetation. This is just illustrative. They're not exact, but I'm just trying to get something from there. And then we would have, but that is because the different surfaces have different reflectances in that particular wavelength. So when it comes to mapping, we want to identify and distinguish different surfaces. And why is that important? The applications are numerous. We want to identify different vegetative surfaces, or we want to identify different land covers. Why is that important? It helps us with the mapping. We want to come up with the land cover maps of our different areas. We want to appreciate trends. So if I have a map of, let's say, I want how have changed over time, I can get a satellite image of 1995. 1995. 5. We can see what the wetlands were like in 2005, 10. We can now look at the acreage of wetlands in the place of interest. Maybe it was 4,500. Here it was 4,000. Here it was 3,000 square kilometers. Maybe here it was. We can also distinguish built-up area. Maybe here it was 1,000. Maybe here it was 5 square kilometers, 7,000, 1,000. So you can classify your map according to extract features of interest, and that's one of the exercises we shall be involved in. So you get an image of 1995, 1000, 2005, 2010, and the beauty with satellite imagery is that you want to be able to make projections. So we can have area and look at your different years, and can have 1995, 2000, 2005, 2010, and we can maybe see that there is a negative trend. And the beautiful bit about this is that we can even make, so that's how we say that by 2020, if we don't do anything to preserve our wetlands, the wetlands will have diminished. But how are we able to make those conclusions? We make conclusions by distinguishing the different features on the different maps throughout the different times, and we get an assessment. We could also do the same for built-up area. Same time, we look at area, and we go to the years, and we can now model how fast our cities are growing. So that is an example of mapping applications, and with mapping, we want to identify different features. We want to identify different features from one another. We want to see where the wetlands, where the built-up area. We can also do forestry application. We can also do urban sprawl. How is the city growing? Sorry, there was a bit of background noise. Yeah, so those are examples of mapping applications. When it comes to modeling, the idea behind modeling is that we take a measurement, and so we get digital numbers, and we can relate this to reflectances. But ultimately, we want to establish a relationship between reflectance and a biooptical parameter. So, for example, we have been doing work on Lake Victoria. We are measuring reflectances, but we want it to give us an idea about a water quality parameter, chlorophyll A. So we are not measuring chlorophyll A. We are trying to establish a relationship between reflectance and chlorophyll A. Or we want to see a relationship between reflectance and what we refer to as, so we are not measuring the depth by analyzing the light that the satellite captures. Remember, the satellite is measuring what is coming out of the surface. Yes, I'm talking about a case where the surface is water. Different constituents, different pollutants will influence the amount of light that the satellite captures. And so we want to establish a relationship between what the satellite captures and the nature of what is in the water. Now, it's important to observe that not all water quality parameters can be measured. We essentially are interested in parameters which change the color of the water, because that we can measure from space. And by looking at that satellite image, we are able to come up with ideas of water quality parameters. So that's what we mean by optical model. We measure reflectance, but we use reflectance to give us an idea about a biooptical. That's an example of biooptical modeling. But where does it come from? It comes from the fact that we have radiation, which comes from the sun. We have energy interactions on the atmosphere. We eventually have energy interactions on the Earth's surface. But what is of interest for us, we're interested in reflected energy that is captured by the satellite. Now, remember, we are trying to make an impression, get an impression of the Earth's surface based on what is captured from the Earth's surface. So if it is on the Earth's surface, we are able to distinguish different surfaces. If it is from water, we can do biooptical modeling, and the list of applications is numerous, is endless. Yeah. So we need an appreciation of reflectance, because it gives us a ratio of reflected energy to incident energy. And as you can imagine, if we had an image here, it would mean that if you looked at that image, the brighter area would be soil. Brighter images would be then. So what we're trying to say is that depending on where you look in the electromagnetic spectrum, chances are that we will see different things. Of course, we have cases, see that, where vector is the same. What do you think is going to happen when you look at this image? So what do you think this image would look like where we have soil and vegetation having the same reflector?
Maybe we can't tell them apart.
Actually, that's the right answer, because when you look at this image, they will have the same values and won't be able to distinguish them one picture from the other. And so the whole idea behind remote sensing is about juggling. Which bands do we use? And we shall look at that more in the next lecture, because in the next lecture we shall now be we have moved from the sun energy interactions in the atmosphere, energy interactions on the earth surface. We shall now be focusing on the intricacies there. Yeah. So what is happening here is that at this point, those two surfaces cannot be distinguished because they have the same reflector. But yeah, that's the exciting thing about remote sensing, and we will get a fuller picture when we start doing some of these hands-on. I have a clip I would like to share with you, and hopefully it will shed more. It will help bring together what we have looked at, and I need to first share the link with yesterday through your class rep. I shared the link to about what we covered yesterday. I hope you have had time to go through it. All of these, about helping you appreciate these concepts better. So let me get this working, and hope you will do it. And if you have any questions, feel free to.
Hello everyone, and welcome to this sixth lecture in this course. There is introduction to remote sensing, and in this particular topic we will be discussing the interaction mechanism of electromagnetic radiation with the objects which are present on the ground, especially vegetation, bare soil, water bodies, and their response curves, spectral response curve, which we will see how these curves of different objects at different wavelength they behave. For example, when there is when this radiation, solar radiation interacts with the target, an example here of vegetation, and there might be reflection from the vegetation, there might be some absorptions of solar energy by the plants, and there might be transmission. So all these three things will keep occurring, whereas leaves, especially if they are having chlorophyll content, then they will have a different response in a visible part compared to the infrared channel, and so on, as we can see in this small spectral curves of three types of objects which are shown here, and these are more or less standard spectral curves, wavelengths on the x-axis, and reflection in percentage is given in the y-axis. But we see that the bare soil, which shows the maximum reflection around 1.4 to 2.6 micrometer, and whereas the vegetation, which is very important to notice, that suddenly around 0.7 jumps, and it shows the very high reflection compared to other parts of EM spectrum, whereas the water only shows in a very small part of EM spectrum some reflection, and then there is a sort of complete absorption. So all these reflection, absorption and transmission phenomena will occur together, and different objects in different part of EM spectrum will behave differently, as we are seeing here. We will see these things in much more detail. That radiation that is not absorbed or scattered in atmosphere can reach and interact with the earth. And so remember that when the solar radiation is coming, some portion of that is absorbed within the atmosphere, but remaining part may reach to the earth surface and can interact with the objects which are present there. And the three forms of interaction can take place when the energy strikes, or it is the incident upon the surface. And these three are absorption, which we have discussed, transmission and reflection. So the total incident energy will interact with that surface in one or more these three ways. The proportions of each will depend on the wavelength of energy. That is very, very important. and the material and the conditions of the feature. Conditions of the features means if the vegetation is very healthy, having high chlorophyll content, it will behave differently, but the same vegetation, if it is not having, it is drying up or having some disease, it will behave differently in different part of EM spectrum. So that is why it is mentioned is the condition of a feature. Now this radiation or interaction, there might be two ways that one is this reflection, and there might be a reflection by the man-made surfaces or some natural surfaces, and which we call as a specular reflection, and there might be a diffuse reflection which may be because of vegetation, maybe bare soil, some rocks and other things. So these will affect the signatures or their presence in the satellite images at different bands. So two types of reflection which are observed, mainly which are two extreme ends in the way energy interact and reflected back. One is specular and reflection, maybe from the roads, maybe from a calm water surface and so on, whereas the diffuse reflection may be from vegetation and other. So specular reflection, the maximum energy is reflected back, whereas diffuse reflection, some and it is scattered all around. So when a surface is smooth, we get a specular or a mirror-like reflection, where all or almost all of the energy is directed from the surface is in the single direction. Whereas diffuse reflection occurs when the surface is rough and the energy is reflected almost uniformly in all directions. And most of the earth features which are not really perfect specular reflectors or neither diffuse reflectors. So most of the features falls in between of these two categories, and whenever a particular target reflects specularly or diffusely or somewhere in between, depends on the surface roughness of the feature in comparison to the wavelength of incoming radiation. And the example here is that if wavelength is much smaller than the surface variation or the particle size that make up the surface, diffuse reflection will dominate. For example, the fine-grained sand, especially present in the desert areas, would appear fairly smooth to long wave microwave, but would appear quite rough to the visible wavelength. So it depends, the same surface, but depends on the wavelength, in which wavelength or in which part of EM spectrum you are looking, or which band of the satellite image you are looking. The same object may look very smooth or in larger wavelengths, but may look rough in visible. Similarly, the leaves, plant leaves, the chlorophyll strongly absorbs radiation in the red part and the blue wavelengths, but reflects green, and that is why we see in the visible part, when that is why we see vegetation, healthy vegetation generally green, because the red portion and blue portion are absorbed, whereas the green is reflected. And leaf appears greenest to most of us in summer when chlorophyll content is at its maximum, depending on the season of different areas in the country or world over, whereas in the autumn when there is a less chlorophyll content, so there is a less absorption and proportionally more reflected of red wavelength, and making leaves appear either yellow or red, and yellow is a combination of red and green wavelengths. So when chlorophyll is less, then the green is not reflected, and whereas red is reflected or yellow or green is yellow. Similarly, in this healthy vegetation act as a excellent diffuse reflector of near infrared bands and infrared wavelengths, and that is why though in our eyes it's different, but in infrared radiation, in infrared bands, the vegetation is having maximum reflection. So our eyes were sensitive to basically to near infrared trees would appear extremely, if at all these our eyes would have been. But we are having sensors in near infrared, and therefore we get very high reflection. And in fact, measuring and monitoring the near infrared reflection is one way that scientists can determine how healthy or unhealthy vegetation may be. And this people exploit, especially for crop estimations or health of a forest area and so on and so forth, that if you are getting very high reflection through infrared channels of an area which is completely vegetated or having some agricultural crop, we can assess that that area is enjoying good growth of plants or a good chlorophyll content are present in the leaves. But if this near infrared reflection is less, then there might be some problem with the plants. As you can see that these are the plants seen through the infrared channels, and they are showing very high reflection, whereas the roof of a house or windows are showing very low reflection. So this property of plant we exploit in our remote sensing and data, and we use the combination to create certain products which we can apply for different kind of application. Now we take the water, then longer wavelength visible and near infrared radiation is absorbed more by water than the shorter visible wavelength. As you saw earlier in the spectral curve of water, in the shorter wavelengths there is some reflection by the water. Otherwise, in the longer wavelength it is completely absorbed, and you can see here also that this is completely absorbed. Thus, water typically looks blue or blue-green due to stronger reflection at these shorter wavelengths and darker if viewed in red and infrared. So whenever we see the infrared images in which the water bodies is present, generally if water is pure, it will completely appear black or dark because of there is no reflection in that part of EM spectrum. Whereas if we look the visible part or shorter wavelength, we might see some reflection of water, especially in the blue portion of EM spectrum or blue or green. That is why we see generally water. So you know that pure water doesn't have any color, but these colors are coming because of reflection in the different part of EM spectrum. And if there are suspended particles present in this upper layer of water body, then this will allow better reflectivity and a brighter appearance of the water. So if it is not pure, like here suspended particles are shown here, then you will get a larger reflection in these parts, and same maybe little more in the red, and infrared may be less. So this kind of changes occur when we are having suspended sediments, or we also call it turbidity present in the water bodies. And this is the example is shown here, and this is the delta which is shown here, and this Ganges and Brahmaputra basically are coming here, Sundarban delta, and they are bringing sediment and mixing with this Bay of Bengal. And what is happening because of this presence of suspended particles and due to that high reflection, especially in the blue part of EM spectrum, and therefore in a Landsat TM near real color images we see a blue portion, and that directly indicating high concentration of sediments present, whereas when you don't have much sediments present, then hardly you are having reflection, and therefore they are in true color images they are appearing as black. So this is how interpretations can be made of satellite images. Whereas the green is of course vegetation, and there are water bodies, inland water bodies, which may not be having much suspended particles, and therefore they are appearing. So the quality of water can also be assessed through such interpretations of satellite data. As I have already mentioned that suspended sediments which shown here can be easily confused with the shallow but clear water, since these two phenomena appear very similar. That means that if water conditions are very shallow, then the bottom of say there is a lake, it is very shallow, then the bottom of the lake will also reflect. So one should not get confused with that kind of thing, that the shallow, the less column of water may also reflect, whereas at the same time the suspended particles can also reflect. So one has to ground check whether this is because of suspended particles or shallowness of a lake or water body. And in normal conditions one may find the algae and other things which are present in the water, which will again, because algae might be having chlorophyll. Chlorophyll in algae absorbs more blue wavelength and reflect green, making the water appear green in color when algae is present. And this type of growth of algae, especially in seawater, and detection of these algae is used to find certain type of fish which may prefer that kind of algae. So this is how remote sensing can be employed to find a certain type growth of algae, and then associated fish might be, and sometimes the undulations or ruggedness or topography of the water surface, that is if it is not standard still water, rough, or depending on rough or smooth or floating material, etc., can also lead to complication for water reflected interpretation due to potential problems, specular reflection and other influences on the color and bright. These curves is spectral curves of three main very standard curves, which we have seen already in a small portion, that generally the water will reflect only in the shorter wavelength near 0.4 to 0.7, 0.1 or 2, and then it is completely absorbed. So only in the first part of visible part of EM spectrum, and maximum you would see around blue, that is why pure water in a deposit may appear as blue. Whereas bare soil, it increases very smoothly, and in mid-infrared it reaches to the maximum, and therefore you don't see much reflection of bare soils in the early part of EM spectrum, especially visible and near infrared. Whereas the vegetation is having altogether different. There is a absorption of vegetation, but starting from 0.7 to about 1.2 or 1.3, it is having the maximum peak, where you get the maximum reflection by the healthy vegetation, green vegetation, and if there is the vegetation is not healthy, then there might be a shift in this curve, and the curve may shift towards the left. So we also use this to find out whether vegetation is healthy, enjoying good health, chlorophyll content is normal or abnormal if there is not high reflection which one is getting in near. So by measuring the energy that is reflected or emitted by the targets on the Earth's surface over variety of different wavelengths, we can build up a spectral response for that object. These are the standard generalized spectral curves of three different types of Earth objects, which you are seeing here. By comparing these response patterns of different features, like here soil, vegetation and water, and we may be able to distinguish between them. As you can see that all three different objects are showing completely different signatures or curves or behavior in this part of EM spectrum, especially in visible, near infrared and mid infrared. As we have seen that the like water and vegetation may reflect somewhat similarly in visible wavelengths, but are almost always separable in infrared. So in one particular channel or in band, you may not differentiate certain objects, two objects, but if you start looking the different channels, you will find a completely different signatures or their pixel values completely different in different channels. A spectral response can be quite variable even on the same target type, and can also vary with the time, especially about talking about the vegetation. So the same vegetation may reflect differently in different season of a year. So understanding of these factors which influence the spectral response of features of interest are critical, and that makes once we start understanding these spectral curves of different features, especially in mineral exploration or in other mapping, then we can make our interpretation much more reliable. Here a few more curves have been also added, and then corresponding bands or channels of different few satellites are also shown, mainly spot and land. So let me go one by one. That when you are having clear water lake water which is standstill, clear means you don't have the suspended particles, you may not be having any algae or any chlorophyll content, then the maximum reflection will come around 0.6 micrometer, and then there is a total absorptions in beyond this range. Whereas if water is turbid, that means there is a turbidity, there are suspended particles are present, then the reflection may continue even up to 0.9 or very close to 1. Even in near infrared. Similarly, in case of wet soil or dry soil, this behavior of these soils, depending on the content of water, they may show completely different reflection curves. As we can see here, that initially they are showing like dry soil will always have more reflection as compared to wet, And there are some portions where you are having the maximum difference. So two examples are shown: 5% water, dry soil, and which is we consider 20% wet is a one. And so as soon as the soil becomes wet, it is showing a less reflection in almost in the between 0.4 to 2.4 micrometer throughout this visible near infrared and mid infrared region. Whereas vegetation as if it is healthy vegetation, it will show very high reflection between 0.7 to 1.1 or 1.2 micrometer, and in between also there are some other peaks are there, but otherwise this is the standard one. So when initially when the Landsat 1 was designed, that is we also called as ERTS, and the sensor MSS, at that time these bands had the same width and a continuous. So like 0.4 to 0.5, 0.5 to 0.6 like. But later on it was realized that such approach is not good, and therefore wherever for whichever phenomena which we were looking to discriminate, or the objects which we wanted to discriminate very easily, so then these bands and their width were changed. Like in case of Landsat TM band, as you can see that Landsat 1 and 2 are in the blue and green part, 3 is the in the red part, then 4 is having much more larger width compared to 3, and 3 is having very thin band compared to 1, 2 or 4. And then because of in between nothing was kept, because if one is looking the vegetation, then the band 4 is the best in that sense. If one is looking for water bodies and other things, then 1 and 2 or even 3 up to 3 are. So then a large gap in EM spectrum was left, and then the fifth one was kept here to see the differentiation and especially another peak of the vegetation, and then again band 7 was kept here again to catch the peak of wet soil, dry soil as well as, but in between 5 and the large gap was left. Band 6, which is missing here, falls in the thermal infrared part, that is why it is not shown here. Whereas in case of SPOT, which was a French satellite, multispectral bands which are quite similar to the Landsat TM bands, but there is some shifting of band 1. Instead of starting from 0.4 or 0.45, it really started at 5.5 to 0.6, and a very small gap between band 1 and 2, but there is some gap between band 2 and. So later on people realized that based on these spectral curves, instead of having continuous bands and having uniform thickness bands, it is better to have bands based on these spectral curves where we can discriminate or record these different objects which are present on the way, rather than having uniform slicing and same size of or a location or a continuous. So that was a intelligent move later on, once people realize through the experience of Landsat MSS. So this brings to the end of this particular topic about how this solar radiation interacts in different part of EM spectrum with different objects which are present on the surface of the earth. We mainly focus on the water body, bare soil and vegetation, and how these absorption phenomena and atmospheric windows which are available, and how different satellites and their sensors have been designed and kept at different locations, so we can capture all the important features or objects which are present on the surface of. Thank you very much.
Okay, so hopefully that has given us a good appreciation of what we have been talking about. As you have heard, in remote sensing, our interest is either mapping. We want to identify or distinguish between different surfaces. Our ability to distinguish between different surfaces is based on the fact that every surface has a unique spectra. As you saw, different vegetative surfaces have different spectra. Dry soil has a different spectra from wet soil. The percentage of water in the soil also has a bearing on what the spectral signature is about. And by looking at different portions of the spectrum, we're able to distinguish between different surfaces, which is one of the very, very important applications of remote sensing. we want to map, we want to identify, we want to discriminate different features from the other. So I like saying that in remote sensing, we are essentially having a paparazzi in space, photographer in space. So when we take that picture, can we identify the different features? How are we able to distinguish the different? Our ability to do that is based on the fact that different surfaces have different reflectances, and that is how and why we are able to distinguish between the different surfaces. The other application is bio-optical modeling, and here we are relating that pixel value to a particular bio-optical parameter. So if you remember the picture where he was talking about sediment, we have two applications. We can distinguish sediment areas from the non-sediment areas, but also, and that would be mapping, that for bio-optical modeling, we would be saying, can we determine the concentration of the sediment from what we are able to see? So those are the two aspects we need to be conversant with, and these are some of the other applications. And so that brings us to the end of our discussion on energy interaction on the Earth's surface. So with that, we come to the close of our class, and if there are any questions, I will be happy to field them. Any questions? Okay. If there are no questions, I'd like to bring this class to an end. And all right, so have a good evening, and let us touch base tomorrow and continue our class on remote sensing. So thank you. Have a great evening.